Hi, I'm Thomas Ortner from the ESA Research Center in Vienna. Welcome to my talk on InCorr, Interactive Data-Driven Correlation Panels for Digital Outcrop Analysis. Previous and ongoing missions on Mars were focused on looking for signs of water. There is strong scientific evidence that there have been lakes and rivers on the Martian surface. Based on that, the upcoming rover missions by ESA and NASA seek signs of past life, so-called biosignatures. The geological analysis of 3D digital outcrop models is a key aspect in this endeavor. It allows geologists to reconstruct ancient habitable environments and ultimately decide for drill sites where a rover might actually pick up biosignatures. An outcrop is a location where a piece of rock exposes different layers, so-called strata. The vertical succession of these strata is a chronological view into the past of a planet's surface. In this example, we have a terrestrial outcrop from southwestern Utah. And as we can see, where Utah is a hotspot for field trials and Mars analog experiments. Traditionally, geologists make measurements in the field using hands-on tools. Affordable remote sensing solutions have made the geological analysis of digital outcrop models very popular. It reduces the fieldwork to capturing the data, and the actual interpretation on high-resolution 3D reconstructions of surfaces can be performed in the comforts of one office. These methods can be applied to stereo image data collected by rovers on Mars, and the resulting DOMs can be used to greatly enhance our understanding of the evolution of the planet's surface. First, geologists are interested in contacts. These are the discrete transitions between strata. Contacts can be numerous and have different magnitudes, depending on the magnitude of change between strata. Strata are arranged hierarchically, as for instance, here we have a couple of bed sets bounded by orange lines, which are substrata of units bounded by red contacts. Another important aspect are crossbeds. These are features preserved from their time of deposition. The interpretation of the dip direction of crossbeds, indicated by the arrow disks, is invaluable to reconstruct the direction of ancient wind or water flowing. After interpretation, geologists want to summarize an outcrop in a sedimentary log. A log illustrates the succession of strata and relevant geological properties, such as rock type and deposition direction. The y-axis shows the elevation of contacts, consequently the thickness of the enclosed strata. The x-axis is a logarithmic scale representing the grain size of a stratum's rock type, from fine clay to coarse gravel. The color of a stratum in the log represents its rock type category. To characterize the orientation of a stratum, geologists use Rose diagrams, showing the angular distribution of crossbed measurements. It has to be noted there is no accepted standard for what a log should look like except the encodings we just discussed. Inspiration for this work was the Dinosaur Quarry campaign. Our collaborators, leading planetary geologists, went to Hanksville, Utah in the course of a Mars field exploration and captured 4 outcrops digitally. They interpreted the digital outcrop models, created logs, and finally arranged them in a correlation panel, which looks like this. We cannot go into detail here, but the juxtaposition of logs allows geologists to identify similar strata across outcrops. Connecting these strata, as here with the red stippled lines, is called a correlation, giving the panel its name. Such a correlation analysis is essential for building a regional geological model and is also a typical result in geological publications. This representation has several shortcomings. Logs and correlation panels are illustrated manually. This is very time-consuming, and it's also very painful to adapt and extend these illustrations afterwards. Further, there are no interpretation tools which directly support the logging or the drawing of logs. Usually multiple tools are involved, and there is no backlink to the original data. Finally, this is a static one-shot representation, which makes it very difficult for other geologists to reproduce the results of a correlation analysis. We came to the conclusion with our collaborators that they would greatly benefit from an interactive correlation panel. It should look familiar, looking like manual illustrations, but should also be cheap to create and to maintain. In the form of a design study, we researched two components: a 3D logging tool to efficiently connect contacts, and the InCorr panel, short for interactive correlation panels. We evaluated our results through a use case. We also compared our result to manual illustrations, and we asked 3 geologists to give feedback on our designs. Ultimately, we present an approach that could change the way how geologists work with digital outcrop models. Luckily, our collaborators already approached us with a simplified form of a log, and this closely matches our final result of a geological log created with InCorr. InCorr supports all the tasks necessary, going from the interpretation stage to a finished correlation panel. To create a log, users can connect contacts and derive strata from that. Each strata can be assigned with a rock type and several crossbed measurements. The logs are then arranged in the correlation panel, which allows geologists to find similar strata. Then they can connect the contacts and derive correlations. Finally, they can vertically align the geological logs and export the illustration for publication. We integrated the 3D logging tool into the interpretation software Pro3D, and we also added the InCorr panel and a graphical user interface for assigning rock types. To create a log, we first need to pick a reference plane for height computation. Then we pick 3D points on the individual contacts to add them to our log. These points, or the contacts actually, are sorted per height, so we can pick the contacts out of order. Also, a contact exists only once per log, so we can easily adapt or extend our 3D geological log. After selecting the contacts, we receive an empty geological log. In the next step, we want to assign grain sizes to individual strata. Therefore, we select a stratum and then we select a rock type. The selected stratum is indicated by highlighting the bounding contacts. In a similar way, we can assign crossbeds to the selected stratum by selecting it first and then selecting the crossbeds we want to add. On confirmation, we receive a rows diagram right next to our stratum in the log. Here we see the result of our use case, the 4 outcrops of dinosaur quarry. We created 4 logs connecting 60 contacts and assigning 130 crossbed measurements. Below we can see the logs arranged in the correlation panel. The InCorr panel supports zooming, panning, and vertical stretching of the logs. To create a correlation, we simply select contacts across the logs and connect them with a correlation line. After creating another correlation, we can select the first one and arrange the logs vertically. This is typically found in geological journals. Finally, our correlation panel can be exported and brushed up for publication. Creating these logs of dinosaur quarry, 3D and 2D, took us 1.5 hours, although we took 5 times as many measurements as in the original dataset. According to our collaborators, a comparably detailed analysis would take a whole day or even several days. Further, we invited a sedimentologist dealing with mass data, an engineering geologist working on tunnel data, and a planetary scientist with a strong geological background to evaluate our designs. I will now present you with some quotes from the feedback sessions. Looking at the software, I should be able to do this very quickly, in about an hour instead of a week. The highlighting of a stratum's contacts is very intuitive. It looks visual and haptic. This is perfect for correlating spatially over large distances. And concerning the data-driven aspect of our work, isn't this the whole point of a publication? To have other people interact with your data. I hope that is the future of publishing. So, what did we have to leave out in this talk? What is more in the paper? I concealed from you the algorithm on how to derive strata from contacts, and there are also some interesting details about the design process. As previously said, we conducted an in-depth comparison of the manual illustrations and our InCorr panel. You might also wonder, why do we need a reference plane? And you might also be hungry for more geology. In conclusion, we translated a static illustration to a data-driven dynamic one. We speeded up the workflow of geologists working with DOMs by a factor of 10 to 20. We introduced WIS to the domain in sedimentology and stratigraphic analysis, and also vice versa. I hope you enjoyed this talk, and I'm happy to take your questions now.